Now let us solve few miscellaneous types of sums based on inverse trigonometric functions. Now in this question we have to show that cos inverse of 4 by 5 plus cos inverse of 12 by 13 is equal to cos inverse of 33 upon 65. Now on left hand side, if you observe, we are given basically two angle quantities, isn't it? Cos inverse of 4 by 5 if you call it as alpha, and cos inverse of 12 by 13 if you call it as beta. Then the sum of two angles is equal to cos inverse of 33 upon 65. So in other words, if we prove that cos of alpha plus beta is equal to 33 upon 65, then our job would be done. Okay, now let us assume cos inverse of 4 by 5 as alpha. So that means, in other words, cos alpha is nothing but 4 by 5 and cos beta is nothing but 12 by 13. Right. So from this we can readily calculate sin alpha as 3 by 5 because 3, 4, 5 forms the Pythagorean triplet, and in case of beta also we can say that sin beta has to be equal to 5 by 13 because 5, 12, 13 is also the Pythagorean triplet. So we have got all the four important pieces that we need to calculate cos of alpha plus beta. So now let's go ahead and evaluate cos of alpha plus beta. That is equal to cos alpha cos beta minus sin alpha sin beta. Okay. Now cos alpha is 4 by 5 into cos beta is 12 by 13 minus sin alpha is 3 by 5 into 5 by 13. So that is 48 upon 65 minus 15 upon 65. So that gives us 33 upon 65. So here you see we got cos of alpha plus beta to be equal to 33 upon 65. So therefore from this we can say that alpha plus beta is nothing but cos inverse of 33 upon 65. And substituting the values of alpha and beta, we will get the required relation proved. So that's the proof. Let's see another example. Solve the equation 2 tan inverse of cos x is equal to tan inverse of 2 cosec x. Alright, now here if we think a bit, first of all there are two tan inverse terms on both the sides, but because of this factor 2 we cannot eliminate the tan inverse of terms right now. So let us try to convert the left hand side into tan inverse of some expression, and for which we have seen the result that 2 tan inverse of x can be written as tan inverse of 2x upon 1 minus x square. Right. So by writing this we can get rid of this multiplier 2. Okay. So therefore let us start off with LHS, or rather we can just write it here itself. Right. So therefore we can write this as tan inverse of 2 cos x. Now whatever is x here, that is actually equivalent to cos x. So we replace x with cos x in this formula, and denominator is 1 minus cos square x, which is equal to tan inverse of 2 cosec x as it is. So therefore we have tan inverse of 2 cos x upon 1 minus cos square x is clearly sin square x, that is equal to tan inverse of 2 cosec x. So now we can say that removing tan inverse from both sides, we have 2 cos x upon sin square x is equal to 2 cosec x. So 2 gets cancelled. Now you see cos upon sin square can be written as cosec into cot. Right? So one sin isolated gives us cosec, and the remaining term cos by sin is cot, that is equal to cosec. Now you see cosec x is common on both sides, so we can cancel it, but provided we have to prove that cosec x is not 0, because we cannot cancel 0 from two sides of an equation. Now we know that for the cosec function, right, the range of the cosec is that it is either equal to 1 or more than 1, or it is equal to -1 or less than -1. So that's the range of cosec function. So clearly cosec x will never have the value 0. Okay, so since it's guaranteed that cosec x is not 0, so therefore we are allowed to cancel cosec x from both sides. So therefore we get cot x equal to 1, and therefore x has to be equal to pi by 4, that is 45 degrees. So that's the required answer.